students, welcome to my channel CBSE Tutorials by Anjali Arya. So today I have brought to you a one-shot video. It's a complete full revision video for the chapter Classification of Elements and Periodicity in Properties. So this is the third chapter in your chemistry, and in this video I have covered almost all the important topics. So let's start. Now first, what is the introduction of this chapter? What is the need to study this chapter? Now there are 128 elements which were known till now, and it is difficult to study their properties separately. So in order to make the study easy, the classification of elements was done. Now what does actually classification means? Basically, it is the grouping of similar elements together and then separating those elements from those which are not similar. Okay, so many attempts have been made by scientists in order to classify the elements. Like they classify elements on the basis of similar properties. Okay, like they group elements together. So when the elements were discovered, so many patterns were proposed. That is about approximately 2000 or even more than that patterns were proposed to create groups of these elements or to classify them. So initially 31 elements were introduced, then the discovery went to 63 elements, and then to 114, and now more than that. So it is very difficult to memorize the properties of so many elements. Therefore, they have developed some patterns to make the study of these elements easier. So first we will just do a little brief introduction of whatever was the history of classification. Now we have all studied in 10th class about Daubrey's law of triads. Now we know that he had arranged the elements in a group of 3, and this group was known as triads, and he proposed the different triads which was depending upon many properties, and these properties could be the increasing atomic mass, then they were similar in their properties, and the atomic mass of the middle element, that is in the triad, the middle element which was there, its atomic mass was basically the arithmetic mean of the atomic mass of the first and the third element. Okay, so this is what we have done already. We have understood this in class 10, but I'm just doing a brief recap of all that. So example, we had lithium, sodium and potassium in a triad, and in that the middle element's atomic mass is the arithmetic mean, that is the mean of the other two elements' atomic mass on the left and the right. Now one limitation was that he failed to arrange all the known elements of that time in the form of triad. That is, he could arrange only a few elements in the form of a triad, not all the elements that were known at that time. So that was one limitation of his triads. So now let us see the Newland's law of octaves. Now according to him, that is according to Newland, when elements were arranged in the order of increasing atomic masses, the properties of the 8th element was a repetition of the properties of the first element. So basically what it meant that when you arrange the elements on the basis of increasing atomic masses, then every 8th element had properties which was similar to the properties of the first element. So that was Newland's law of octaves. But the limitation of that octaves rule was that he could classify it only up to calcium, because after calcium this rule was not applied. Okay, so that was one limitation. Now let us see Mendeleev's classification of elements. Now according to Mendeleev's famous periodic law, the properties of elements are a periodic function of their atomic masses, and in this there are 7 periods and 8 groups. Now out of these 8 groups, 7 are of normal elements and 1 is of transition elements. And one very important thing about Mendeleev was that he left gaps in his table for the unknown elements of that time. So that was a very big discovery, or that was a very big advantage of that table. Now what was the demerit of Mendeleev's table? See, one thing was that the position of isotopes, it could not be explained. Second thing was that the wrong order of atomic masses could not be explained. Like the elements were arranged in increasing atomic masses, but in some places, like in case of cobalt and nickel, the atomic masses was not in increasing order. Like the one with the larger atomic mass came first, then the other one. So that was in cobalt and nickel, that is one example. Then comes the position of hydrogen. Now the position of hydrogen could not be explained. Now we all know that hydrogen has properties which are similar to that of the alkali metals and then to that of the halogens. So he could not assign a proper position to hydrogen. So that was one demerit. Then some dissimilar elements were grouped together while some elements were placed in different groups. So usually they had to be placed in with similar properties, but then some dissimilar elements were placed together. So that was also one demerit of Mendeleev's table. Now comes the modern periodic table. Now with the modern periodic table came the modern periodic law, which said that according to the properties of elements, all the periodic function of the atomic numbers. Basically, the properties of the elements are a periodic function of their atomic numbers. In case of Mendeleev, it was atomic masses, but in case of modern periodic law, it is atomic numbers. Okay. So this table consists of horizontal rows which are known as periods, and the vertical columns are known as groups. So in this, there are 7 periods and 18 groups. Now how many elements are present in each period? See, first period consists of 2 elements, then the second and third have 8, and then the fourth and fifth have 18, and then sixth period has 32 elements, and then seventh period has the rest of elements. Okay, so this is basically a general order for a general keeping in mind that how many elements were present in each period. Now this is a very important slide. Now this talks about the families of different elements, basically what do they belong to. Like if you talk about the first and the second group, then from 13th to 17th group, these group elements are called as representative elements or normal elements. Now this is important. Okay, these are called as representative elements or normal elements. Which group elements? The first and second group, and the 13th and the 13th to the 14th group elements. Then from the 3rd to the 12th group, the elements are called as transition elements. Okay, they are D block elements. Now we'll talk about the blocks also in the coming slides. Then from 57 to 71 you find lanthanoids, and then from 89 to 103 you get actinoids. Now when you talk about the periodic table, the left side of the periodic table mostly consists of metals, and the right side one consists of non-metals. Okay, and then there are metalloids also in between. So in the periodic table mostly you find metals, and they're concentrated towards the left side, and then on the right side you get non-metals as well as metalloids. Then one more thing about hydrogen is that hydrogen, the element hydrogen, has been placed at the top of first group because electronic configuration of hydrogen is similar to that of alkali metals. Okay, we know that electronic configuration of hydrogen is 1s1. So it is similar to that of alkali metals. That is why it is placed at the top of the first group. Now let us see the IUPAC nomenclature. Now what happens? Okay, 1 minute. Yeah, so now what happens in this IUPAC nomenclature? Now what is this IUPAC nomenclature for? Now the elements in the periodic table whose atomic number is 100 or more than 100, to name those elements we use this IUPAC nomenclature, because if you have so many elements you can't remember the name of each and every element. So we have got one system of remembering the names of or naming those elements. Okay, now this is the abbreviations or the names. Like if you have 0, the name will be nil. If you have 1, it will be un. Okay, for example, I'll take an element whose atomic number, let it be 105. Okay, now in this you can see the first number is 1. Now for 1 you have this name un, so you will put 1 un. Then for 0 you have nil. Okay, so you will put 1 nil. Then for 5 if you check you have pent, so you will put 1 pent over here. Now after writing all these 3 you will put IUM in the last, and the name becomes un nil pentium. So this is how you name the elements in parts. Okay, like they have got 3 numbers. So first number is 1, so for 1 you have un, so I have written un over here. For 0 you have nil, so I have written nil over here. Then for 5 if you check you have pent, So I've written pent over here. So after writing all these, you have to add IUM in the last. This is the same case for all the elements, okay, after 100 atomic number. So then the name becomes un-nil pentium. So that is how we name the elements whose atomic numbers are 100 or more than 100. So this is the periodic table, okay. Now you can see the S block elements, the D block, P block and the F block elements, okay. Now we will talk about these elements and their electronic configuration now. So okay, so let's start with the S block elements. Now it is very simple how to know whether which element belongs to S block, P block, D block or F block. Okay, it is very simple. Like if the element enters if the last electron of that element enters the S orbital, then it is S block. If it enters the D orbital, it is D block. If it enters the P orbital, then it is P block. If it enters the F orbital, then it is F block. So it is very simple to know the blocks, okay, to which block the element belongs to. Okay, like over here also you can see that element in which the last electron, okay. Now if you know how to write the electronic configuration, now the last electron, if it enters the S orbital, then it belongs to the S block. And if in the exam people mostly ask about the general electronic configuration, okay. So the general electronic configuration of S block elements is NS1 to 2, okay. You write it like this, NS1 to 2, right, because it can be NS1 or it can be NS2, okay. So this is the general electronic configuration. So usually in exams they ask that what is the general electronic configuration of S block, P block elements. So for that you have to write this, it is NS1 to 2, okay. So that is the general electronic configuration. Now comes P block elements. Now the elements in which the last electron, it enters any one of the 3p orbitals. 3p in the sense I am talking about px, py and pz. Or else if you don't want to go in detail also, you can just say that if the last electron enters the p orbital, then that element belongs to the p block, okay, as simple as that. Now the general electronic configuration, outer shell configuration of this p block elements is NS2 NP1 to 6, okay, except for helium. Now I'll tell you why except for helium. Okay, so first if they ask you for the outer configuration, you can write NS2 then NP1 to 6. Okay, so in the exam if they ask you what is the general outer shell configuration of the P block elements, then you have to write this. This is important, okay, this is important. It is NS2 NP1 to 6, okay, that is that NP can vary from 1 to 6 depending on how many valence electrons are present in the last shell. Now why in case of helium is, now you know helium's atomic number is 2, okay, so its electronic configuration will be 1s2, it cannot be more than that. Now here you can see that the last element, the last electron of this element is going to the s orbital. Now you will say that since it is going to the s orbital, it belongs to the s block, but that is not the case. Helium belongs to the p block elements. Now here helium is an exception. So that is why this outer shell configuration is for all the elements of S block except for helium, because helium has this for P block, sorry, except for helium, because helium has this S block kind of configuration, but it belongs to P block because it's the properties of helium are similar to that of P block elements, okay. That is why it is placed in P block, though its electronic configuration is like the S block elements. So that is one exception. Now also about hydrogen, I wanted to say that hydrogen neither belongs to S block nor P block. It has given a special place, okay, because you know that the properties of hydrogen varies. So we have got a different chapter also on hydrogen in class 11, there you will study about this. Now here comes the D block elements. Now the elements in which the last electron enters the d orbital, then that element belongs to the d block, okay. Now the outer general configuration of d block elements is n-1 d 1 to 10 and ns 1 to 2, okay. So you write it somewhat like this, that is in superscript d 1 to 10, okay, n-1 d 1 to 10, then ns 1 to 2. Okay, n minus 1, d 1 to 10, and then ns 1 to 2. This is the general outer shell configuration of d block elements. Okay, now this is also important because they may ask you in exam what is the general outer configuration. Now one more important thing about d block elements is they are also known as transition elements. Like I have said you in the starting only about the transition elements, I told you that the elements from group 3, okay, group 3 to group 12, the elements from the group 3 to group 12, they are called transition elements. Those elements belong to the d block. Okay, so that is also one important thing over here. Now comes the F block elements. Now mostly they don't ask you to write the electronic configuration of F block elements. They might only ask you about the general outer configuration of F block elements. So similar to how the S block, P block and D block we did, over here also it's the same case, that if the last electron of that element enters the F block, then that element belongs to F block. Okay, F orbital, sorry, then that element belongs to F block. So the general outer configuration of F block elements is this. It's n minus 2, then F 0 to 14. Okay, this is in superscript. Then n minus 1, D 0 to 1, then ns2. Okay, so F block elements is not very important. You just have to remember the outer configuration. Okay, this is important. You just remember this thing, that's all, is fine. So the outer configuration for F block is n minus 2, F 0 to 14. It can vary the valence electrons. Then the n minus 1 in D, it can be from 0 to 1, and then ns2. So this is the outer configuration. Okay, now let us see how to determine to which period an element belongs. Now if you know an element's electronic configuration, you can tell to which period it belongs, to which group it belongs. Okay, so let us see how we will know to which period it belongs. Now the largest n value in the electronic configuration gives you the period number. Okay, let me take an example for you. Let us take nitrogen. Now we know that nitrogen's atomic number is 7. So its electronic configuration will be 1s2, 2s2, 2p3. Now if I ask you what is the largest n value in this, the largest n value, if you can see, it is 2. Okay, largest n value over here is 2. So nitrogen belongs to the second period. Okay, as simple as that. Now the largest n value over here, we saw it is 2, so nitrogen belongs to the second period. Now if I ask you nitrogen belongs to which block, can you tell me about that? So just now we have studied that if the last electron enters the p block, then it belongs, p orbital, then it belongs to the p block. So we here the last electron enters the p orbital, so this thing belongs to p block. Okay, so now if you know the electronic configuration of any element, you can tell about its block, you can tell about its period, also you can tell about its group. Now let us see how to determine the group of an element if you know its electronic configuration. See, now first we'll see for the S block elements. Okay, so if you have got an element which belongs to S block, now we know how we can identify an element which belongs to S block. Like we can see the last electron, it enters the S orbital, so that means it is belonging to the S block. Okay, now if you see here, S block elements are only group 1 to group 2 elements. Okay, the group 1 and group 2 elements together make up the S block. Now the number of valence electrons in S orbital will tell us about the group. Now we knew that the general outer configuration of S block was like this, ns 1 to 2, right? So in this there can be two cases, that is ns1, ns2. Now if the outer configuration is ns1, that means it belongs to group 1. If the outer configuration is ns2, that means it belongs to group 2. Okay, that's all for determining the group of S block elements. Now for P block elements. Now the P block elements are the elements that is from group 13 to group 18. All the elements together make up the P block. Now if you want to determine for the p block elements, how will you do it? Like, what you have to do basically is you have to do 12 plus number of electrons in last p orbital. Okay, like that you can determine the group. Now I'll show you an example of nitrogen also over here. Now the electronic configuration of nitrogen is 1s2, 2s2, 2p3. Okay, atomic number 7. So this is the outer configuration of nitrogen. Now how to determine to which group it belongs? So this is like a formula kind of a thing which is important. Okay, you must know this, you must remember it so that you can find the group. Now what you have to do is you have to add 12 plus number of electrons in last p orbital. Now here the last p orbital is this. So how many electrons are there in last p orbital? 3 electrons. Okay, so you will do 12 plus 3 electrons because 3 electrons are present in the last p orbital. So when you do 12 plus 3 you get 15. So nitrogen belongs to the 15th group. Get it? Now if you check, nitrogen is present in the 15th group, just to cross check. Okay, so that is how you determine for the p block elements. Okay, now let us see for the d block elements. Now the d block elements, I just now told you that the transition elements, that is from group 3 to group 12 together, make up the d block elements. Now for the d block elements, how will you do it? Okay, now if you have got a d block element, like example we'll take scandium. Now let us write the electronic configuration of scandium first. So the atomic number I have given here is 21. So for that the electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 3d1. Okay, now that is the electronic configuration of scandium. Now what we have to do is the last element, the last electron goes to the d orbital, so it is d block element. Okay, we know that. Now for d block element, how we find the group? We have to do 2 plus number of electrons in last d orbital. That is the formula. So what we are going to do is 2 plus number of electrons in last d orbital. Now this is the last d orbital. Number of electrons which are there in last d orbital is 1. So 2 plus 1, that is 3. So this means that scandium belongs to group 3. Okay, so that is for the d block elements, how you will find the group. So basically if you want to know the group, you should know the block, to which block that element belongs to, because for different blocks you have got different formula like this. You know, you can consider this as a formula. Yeah, so for F block they don't ask you, so that is only till D block. Okay, now let us discuss about the atomic properties. Now what is atomic radius? Now we have all studied what is atomic radius, that it is the distance from the center of nucleus to the outermost electron. Okay, that is the atomic radius. Now what is the trend of atomic radius in a periodic table? Okay, now what is the trend? I have shown the trend over here. This is the trend, that is how, trend in the sense how the atomic radius increases or decreases along a period and then down a group. Now you know about period. Okay, now what happens in a period is that as you go from left to right in a period, the nuclear charge which is there, it increases. Okay, so we have studied this in our lower classes, that as we go from left to right in a period, the nuclear charge increases. Now when the nuclear charge is increasing, the nucleus is trying to pull the electrons towards itself. So when it is trying to pull the electrons, the distance decreases, that is the atomic radius decreases. So that is the trend, that the atomic radius decreases from left to right in a group because the nuclear charge is increasing. So there is more of attraction towards the nucleus. Now down the group it is very simple, that you know that the number of shells keep on adding down the group. Okay, so the number of shells keep on adding, so the distance from the center of nucleus to the last electron keeps increasing. As the number of shells are adding, the distance from the center of nucleus to the last electron is increasing, so the atomic radius is also increasing, right? So that is the trend for atomic radius. Okay, so now comes ionic radii. Now what is ionic radii? It is the distance between the cation and the anion in ionic crystals. Okay, so the trend for ionic radii is also the same as the atomic radii. Okay, now what was the trend for atomic radii? That is, it decreases along a period because the atomic charge is increasing, so it is decreasing, and then down a group the atomic radii is increasing because the number of shells are adding. Okay, so that was the trend. Okay, so here you can see that this is the ionic radii. This is the ionic radii, and if you want to know the atomic radius, this is the atomic radius. That is, you can find it by doing atomic radius r, you can do it by d by 2. Okay, so that is for atomic radius. Now we hear this thing is very important. Okay, this thing is very important. Now what is this? This is the size. Now the size of an anion is greater than that of the normal atom, and that is greater than that of cation. Now how will you remember this? In the sense, you can think like this. Okay, I'm just giving you a trick kind of a thing, that anion, you know, it is a negatively charged ion. Okay, so there are many electrons in this, it is a negatively charged ion. So you can think like this, that in anion there are more electrons, so the electrons will repel each other. Now when they repel each other, they go far away, so in that case the size will increase. Whereas a cation is a positively charged ion, there is less electrons, so there will be less repulsion, so the size will be less. Okay, so that is how you can remember that anion will be greater in size than the normal atom, and cation will be shorter in size. Okay, that will be less in size. Okay, so that is how you can remember. Okay, so now let us come to the isoelectronic species. Now what do you mean by isoelectronic? Okay, now from the name itself you can know isoelectronic means same number of electrons. Okay, so basically the atoms or the ions, okay, it's not only that you can get only atoms, ions also should be included. Okay, otherwise you won't get same number of electrons. So the atoms and the ions with the same number of electrons are known as isoelectronic species. Okay, now let us take one example. We have got neon, then sodium plus and fluorine minus. Now all these three have 10 electrons. Now we know the neon, the atomic number of neon is 10, so it will have 10 protons, 10 electrons. In case of sodium, the atomic number is 11, but here it is Na plus, that is, it has lost one electron and it has become 10, and it now has 10 electrons. Similarly, in case of fluorine, you have got 9 electrons, but since you can see that it is fluorine minus, that is, one more electron is added, so it becomes 10 electrons. So that is isoelectronic species example. Now in case of isoelectronic species, higher the atomic number, smaller will be the radius. Now what does this mean? Okay, if I give you this example and if I ask you that you compare all these three on the basis of their sizes, now how will you do that? See, now you will do that. Now when you see these three, you can see that they're isoelectronic, all of them will have 10 electrons. Now how to know which is larger in size, which is shorter in size? So for that we have to know the number of protons present, that is the atomic number. We know that the atomic number will give us the number of protons. Now what happens in case of Na plus? Now sodium, we know that the atomic number of sodium is 11, so it will have 11 protons. Okay, it will have 11 protons and it is having 10 electrons. So when there are 11 protons and 10 electrons outside, there is more of protons, so there will be more nuclear charge. Now when there is more nuclear charge, this proton will try to attract that electron, and the size of the nucleus will decrease. Okay, size of the nucleus will decrease. Then in case of neon, there is 10 electrons, 10 protons, so it is like a kind of neutral atom. Okay, then in case of fluorine, you can see fluorine, in that I said you that the atomic number of fluorine is 9. So you have got 9 protons and 10 electrons. Okay, 9 protons and 10 electrons because it is F minus. Now what happens when you have 9 protons and 10 electrons? So there is more of electrons, so that nuclear charge is exhibited on each electron, that will become less because there is more electrons. Also there will be a repulsion between electron and electron. So what happens is the atomic radius will increase. Okay, these electrons will go far away from the nucleus because there is less of proton, so there will be less nuclear charge and the electrons will move away. So in that case what happens is the size will increase. Okay, so that is why fluorine size is greater. Also, if you remember one thing, that in the previous slide I had told you that the size of anion, okay, this is a positively charged ion. So this is cation. This is a normal atom, you can say. And then comes fluorine anion. So in the previous one also I said you that anion size is greater than the normal atom, and that is greater than cation size. In the previous page itself I had told you this thing. Let's see what is this ionization energy. Now ionization energy and ionization enthalpy, both of them are the same thing. Okay, some people call it as enthalpy, some call it as energy. Now this is the energy which is required to remove an electron from an isolated gaseous atom in its ground state. So over here, this isolated gaseous atom word is a very important word. Okay, if they ask you to write the definition of ionization energy, then this isolated gaseous atom should be mentioned in that definition. Okay, so basically this ionization energy is nothing but the energy that is required to remove an electron from an atom. Okay, that is an isolated gaseous atom. Now what is this IE1, IE2, IE3? Now this is called as successive ionization energy. Okay, successive ionization energy. Now these are the different ionization energies of one particular atom. It is ionization energy 1, 2 and 3. Now what is this? See, and why did I write this ionization energy of third ionization energy is greater than the second one and that is greater than the first one? Now the reason being that, so now what is the successive ionization energy? For example, you have got one atom. This is the atom, suppose. Now you have to remove this outer electron. So the energy that will be required to remove that electron will be IE1. Okay. Now one electron has been removed and this has gained one positive charge. Now we have to remove this other electron from that. Okay. Now we have got one more electron. We have to remove that. Okay. Now the second time that we are going to remove that electron, the ionization energy that will be required will be IE2. Now what happens is, why is this IE2 greater than that IE1? The reason being that first time when you had removed the electron, okay, it was fine, it was ionization energy 1. Now second time what happens is, now there are less electrons in this. Okay, there are less electrons because you have already removed one electron in IE1. So the second time when you try to remove, already there is less electrons. Now when there is less electron, there will be more nuclear charge which will be exhibited on each electron. Okay, the protons will be same. Now the electrons have become less. So what happens is, the charge that the proton exists on each electron will now increase. Okay, because the same charge but there are less electrons. So this time when you try to remove the electron, you have to put in more energy. More energy will be required to remove the electron. So the IE2 will be greater. Now what happens is, now you have even more less electrons left after IE2. So this time there is even more nuclear charge on that particular electron. So now you have to apply even more ionization energy to remove that particular electron. So that is why IE3 is the greatest, and then comes IE2 and then comes IE1. Because as you keep on removing the electrons, the protons remains the same. Just the electrons are reducing. Now when the electrons are reducing, the nuclear charge that was exhibited on a particular electron keeps on increasing. Okay, because first you had more electrons. Okay, first you had more electrons, so the charge used to get divided on each electron. But now what happens is, now you have got less electrons. So whatever the charge was, it is now on that particular electron, so less electrons. So there is more of those charge on that electrons. So now what happens is, if you want to remove these electrons now, you have to apply more energy because there is more nuclear charge. That is why in the successive ionization energy, the third ionization energy is more, then comes the second one, and then comes the first one. Now what is the trend in this? The ionization energy, it increases as we go from left to right in a period. Okay, 1 minute. Now when we go from left to right in a period, okay, when we go from left to right in a period, what happens is that the nuclear charge which is there, it keeps on increasing. We know that from the starting, that the nuclear charge keeps on increasing when we go from left to right in a period. Now since the nuclear charge has increased, you will need to apply more energy to remove that electron. So more ionization energy should be applied to remove that electron. That is why with the increase in the nuclear charge, the ionization energy also increases. Now when we go down a group, what happens is that the nuclear charge keeps on decreasing, because you know that the shells keep on adding as we go down a group. So the electron goes far away from the nucleus. So the nuclear charge keeps on decreasing because the distance of electron from the nucleus is increasing. So in that case what happens is, since the nuclear charge is less ionization energy is enough to remove that electron. So the ionization energy decreases with the decrease in nuclear charge as we go down a group. So that is the trend for ionization energy. Okay, now so we have got a question over here. We have to compare the first ionization energy of beryllium and boron. Now here in this case, beryllium and boron is an exception in case of ionization energy. Now what happens according to our general trend is that beryllium's atomic number is 4 and boron's atomic number is 5. Now we know as we go from left to right in a period, the ionization energy should increase because there is an increase in the nuclear charge. So we have to apply more energy to remove an electron. We know that. So what happens in this case is that, now according to the general trend, what should be expected is that the left to right, the period is going like this. So the ionization energy should increase like this, which means that the ionization energy of boron should be more than that of beryllium. Okay, that is according to the general trend. But this does not happen. This is an exceptional case. The reason being that if you write the electronic configuration of beryllium, it is 1s2, 2s2, and that of boron is 1s2, 2s2 and 2p1. Now if you see here, the valence electron is in the s orbital. Now what happens is, you know the s orbital is closer to the nucleus. Now here in boron you have got one s orbital and then you have got a p orbital. Okay, p orbital is like this, somewhat shaped like this, tumble kind of a shape. You know that. So when you see, the s orbital is closer to the nucleus and the p orbital is far away from the nucleus when you compare these two. So what happens is, since the p orbital is far away from the nucleus, there will be less nuclear charge on that p orbital. Now since over here we have less nuclear charge, so less ionization energy is enough to remove that electron. So that means the ionization energy of beryllium is more than that of boron, because here in beryllium you have s orbital and here you have p orbital, the last electron. So p orbital, since it is far away from the nucleus, less ionization energy is enough to remove the electron. But in case of s orbital is near to the nucleus, there is more of nuclear charge, so you need to apply more ionization energy to remove the electron. So this was an exceptional case. Okay, so we have got one more exceptional case over here, nitrogen and oxygen. Now what happens in nitrogen and oxygen? Now nitrogen and oxygen, you see the atomic number over here is 7 and here it is 8. So again, same according to the general trend, it should be like from left to right in a period, the ionization energy should increase. So expected thing is oxygen's ionization energy should be more than that of nitrogen. That is expected. But this does not happen, because here this is an exceptional case. This thing is an exceptional case. Now why is it an exceptional case? Again we have to write the electronic configuration and check why is it an exceptional case. Now here the electronic configuration will be 1s2, 2s2, 2p3. It will be 1s2, 2s2 and then 2p3. And here in case of oxygen it will be 1s2, 2s2, 2p4. Now in both the cases we have got p orbital. Now how to say whether it is exceptional or not? Now if you fill the electrons and see here, there are 3 electrons in p orbital and over here there are 4 electrons. Now if you know one thing regarding these orbitals, now you know that half filled, okay, this thing is half filled. So half filled and full filled orbitals, they are more stable. You know that. So over here this orbital is more stable, which means that nitrogen's orbital is more stable. So it will be difficult to remove an electron from that orbital. Since it is already stable, so it will not leave that electron. So you have to apply more ionization energy in this case. You have to apply more ionization energy because it is half filled, it is stable. So in order to remove that electron, you have to apply more ionization energy. So in this case, the nitrogen's ionization energy will be more than that of oxygen. So this is also an exceptional case in ionization energy. Okay, now what are the factors which are affecting ionization energy? Now this is important from the exam point of view. Now we know regarding ionization energy that the more tightly the outer electrons are held, okay, the more tightly the outer electrons are held, the higher will be the ionization energy, because ionization energy is all about removing the outer electron, and if the outer electron is tightly held, you have to apply more energy to remove. So it depends upon three factors. One is the nuclear charge, shielding effect, and distance from the nucleus. Now why is that nuclear charge? Because increased nuclear charge, then you have to apply more energy to remove that electrons. In case of distance of the nucleus also, you can say it is like a nuclear charge only, that if the distance from the nucleus of the outermost electron is more, then less ionization energy is needed, because the nuclear charge on that electron will be less. So less ionization energy is enough. Then you have got one more thing, that is shielding effect over here. Now what is the shielding effect? Now the inner electrons which are there, they tend to shield the outer electrons from the attractive force of the nucleus. Okay, so the more the energy levels between the outer electrons and the nucleus, the more is the shielding effect. So basically what is shielding effect is that the inner electrons which are there, now suppose this is an atom, this is the inner electron, this is the outer electron. So the inner electron, they try to kind of shield the outer electron from the nuclear effect of the nucleus, okay, so from that nuclear charge. So they kind of try to protect it, okay, they try to shield this outer electron from this nuclear charge. So what happens is, when the shielding effect is more, they protect the outer electron more, that is the nuclear charge which will be exerted on the outer electron will be less. So when there is less nuclear charge exerted on the outer electron, less ionization energy is enough, okay, because there is less nuclear charge on the outer electron, so less ionization energy is enough to remove that electron. So when there is more of shielding effect, okay, more shielding effect, less ionization energy, because shielding effect means the inner electron will try to prevent the nuclear charge for going towards the outer electron. So in that case there will be less nuclear charge on the outer electron, and so less ionization energy is enough to remove that electron. Now what is electron gain enthalpy? So this electron gain enthalpy basically provides a measure of energy with which an atom adds an electron to an anion. So with which an atom adds electron to form an anion. Now basically ionization energy was all about removing an electron. Electron gain enthalpy is all about adding an electron. Now the electron gain enthalpy, in this what happens is, it can be exothermic and endothermic. You can classify it into two types. It is mostly exothermic. In one such case it is endothermic also. So what happens in case of exothermic? You know, in case of exothermic the energy is released, and in case of endothermic you supply some energy, okay, that is energy is provided. Now basically what happens is, each time an electron is added to an atom, some energy is released, okay, some energy is released. So each time an electron is added to an atom, some energy is released. So that is called as exothermic electron gain enthalpy. Now what is endothermic electron gain enthalpy? Now if you know about inert gases are already stable. Now when they are already stable, if you try to add an electron to that inert gases, they will not accept it, okay, they will not accept it because they are already stable. So in that case, if you want an electron to be added, you yourself have to apply some energy. You have to supply some energy so that that electron gets added to that atom. So that time the energy is supplied, and that time the electron gain enthalpy is endothermic, okay, because you supply energy to that particular electron, so that particular electron gets added to that inert gas. Okay, so that is how electron gain enthalpy can be endothermic or it can be exothermic. Mostly it is exothermic, but in case of inert gases or these stable gases, it is endothermic, because in that cases you have to supply energy to add that electron. Now what about the trend of this electron gain enthalpy? Now as we go from left to right in a period, the electron gain enthalpy increases. Okay, as we go from left to right in a period, the electron gain enthalpy it increases. Now we know that as we go from left to right, the nuclear charge keeps on increasing. So there is more of chances of an electron getting added to an atom. So in that case, your electron gain enthalpy increases. Okay, so here one more thing is that it increases negatively, and then when it reaches the inert gases, it becomes highly positive. Okay, it becomes highly positive because just now I told you that positive in the sense the energy is supplied and negative in the sense the energy is released. So it was exothermic all the way, it was becoming more and more negative, but then when you reach this inert gases, it becomes positive because you are supplying that endothermic energy. Okay, so that is about the trend. Now since it increases, now you can just remember like this also, that if the electron gain enthalpy is increasing as we go from left to right in a period, the opposite will happen as we go from top to bottom in a group, because you know one more thing, that the shell keeps on adding, so there is more of tendency of losing electron rather than adding electron. Okay, as you go from top to bottom in a group, so the electron gain enthalpy it decreases as you go from top to bottom in a group, but here in this diagram it's just given in the opposite manner. So now let us see electronegativity. Now what is electronegativity? It is the ability of an atom to attract the shared pairs of electrons towards itself. Okay, so it is like an ability to attract the shared pairs of electrons towards itself. Now you must have heard about electronegative elements, atoms. Like fluorine is the most electronegative element in the periodic table. Okay, fluorine is the most electronegative element because it has this tendency of attracting electrons. It is very electronegative. Now when we talk about the general trend, what happens is the electronegativity increases as we go from left to right in a period. Now the reason being is that, you know, again that nuclear charge, same story, that the nuclear charge keeps on increasing. So there is more of tendency of attracting electrons as we go from left to right in a period. So when the nuclear charge is increasing, so you can see in this way that we can relate many things to the nuclear charge. So the nuclear charge is increasing, so there can be a tendency, there can be more tendency or more ability of attracting electrons towards itself. Okay, similarly when you go down a group, what happens is, you know, the shells keep on increasing, the nuclear charge decreases. So the nuclear charge decreases, so the ability to attract electron decreases, that is the electronegativity decreases. So that is the general trend. Okay, so now comes the metallic and the non-metallic character. Now what is this metallic and non-metallic character? Now metallic character in the sense it is the tendency to lose electron. Okay, metallic character means the tendency to lose electron easily, and non-metallic character means tendency to accept electron or gain electron. Now the trend for this metallic character, now the general trend for this is that first we will see for metallic character. Now it is a tendency to lose electron. So it is very clear that when you go from top to bottom in a group, the shells keep on increasing, the electrons will go far away from the nucleus, so the nuclear charge decreases. So in that case the tendency to lose an electron will increase, okay, because the nuclear charge is less. So the metallic character will increase from top to bottom in a group. And when you go from left to right in a period, this will decrease, not increase, it will decrease. When you go from left to right in a period, what happens is the nuclear charge is increasing. So when the nuclear charge is increasing, the tendency to lose an electron will decrease, and as a result the metallic character will also decrease. Now for non-metallic character it will be the opposite. The non-metallic character, that is the tendency to accept electron, will increase as we go from left to right in a period because the nuclear charge is increasing. So there is more tendency to accept electron. And when you go from top to bottom in a period, there is more tendency to lose electron. So the non-metallic character will decrease from top to bottom in a period, and the metallic character will increase from top to bottom in a group. Now what is this diagonal relationship? And this is a very small topic. Now we know that the elements in a particular group, they have similar properties. Okay, all the elements of the first group, they are known as alkali metals. They have similar properties. So the elements that are belonging in a particular group have some similar properties. But in this diagonal relationship, some elements of the second period and the third period have some common properties, some similar properties, and they have some similar properties diagonally, like lithium and magnesium, they have some similar properties. Similarly, beryllium and aluminium have similar properties. Then boron and silicon have got some similar properties. So since like this they have got diagonally, they are related to each other, they have got some similar properties like that, this is called as the diagonal relationship. Because it was expected that in a group the elements should have similar properties, but here lithium and sodium should have similar properties, which they have, but lithium also have some similar properties with magnesium. So that is a diagonal relationship of lithium and magnesium. Okay, now let's get on to oxidation state. Now this oxidation state is defined as the charge that is acquired by an atom on the basis of the electronegativity consideration from the other atoms in that particular molecule. Okay, now let me take an example and explain you. Now you have got CaH2 over here, so 1 Ca and 2 H. Now if you compare, H is more electronegative. H is more electronegative than calcium. Okay, so in that case H is more electronegative, so it will attract the electrons towards itself, so it will acquire a negative charge. And then calcium has to give that negative charge. Okay, calcium has to give those electrons to hydrogen, so it will have to give away 2 electrons. Now when calcium will give away 2 electron, it will acquire +2 positive charge. Okay, because it is giving away 2 electrons, it will acquire positive charge. Okay, and since it gave away 2 electrons, one to calcium, one to both the hydrogens, so it has got +2 charge. Now here the oxidation state of calcium will be +2. Okay, the oxidation state of calcium will be +2 over here. So that is how you get to know about the oxidation state. Okay, so this is like a general comparison of the properties of the S block and P block elements, and this you can say is an important from the examination point of view. So let's see what is this. Now the S block elements are elements having their valence electrons in the outermost s orbital. Now this is like a differences between both of them. This is important, you can note down in your books. Then P block elements are the elements whose valence electrons are in the p orbital. Okay, now what about S block? Okay, the second thing, S block can have 0, +1 and +2 oxidation states, whereas P block can have oxidation states which are varying from -3, then 0 to +5. So it can have those kind of varying oxidation states. Now these S block, they form metallic bonds and they form ionic bonds. Okay, S block elements, you remember, right? Group 1 and group 2 together make up the S block elements, and those group elements, they have this metallic bonds and they have the ionic bonds. Whereas P block elements, what do they do is basically they form these covalent bonds and ionic bonds. Now in S block elements, most of the elements are metals, and in P block elements, most of the elements are non-metals and some of them are metalloids. Now I told you that towards the left side you will find metals in your periodic table, and towards the right side you will find non-metals and metalloids. So towards the right side you can see that you have your P block, and that is why most of the elements in the P block are non-metals and others are metalloids. Now the electronegativity is comparatively less of S block. Now you are comparing S block and P block over here. So electronegativity of S block is less, and here electronegativity of P block is comparatively more. Now since you know that S block elements are towards the left side of the period, so their nuclear charges are comparatively less, so their electronegativity will be less. Similarly, P block elements are towards the right side of the period, so their nuclear charge is more. That is why their electronegativity is also more. Now this was a comparison. This is important. Okay, you can note down this. This is important. Okay. Okay, so let's move on to the next one. Right. So we have got here D block and F block elements comparison. Okay. So D block elements are the elements whose electrons are filled in the d orbitals, and whereas in case of f block, the electrons, that is the valence electrons we are talking about, are filled in the f orbitals. Okay, here in d orbitals and here in f orbitals. Now d block elements, in the starting only I told you that from the elements that is from group 3 to group 12, they are d block elements and they are known as transition elements, and the f block elements are known as inner transition elements. Okay, they are known as inner transition elements and d block elements are known as transition elements. So this is an important point. Now, so when we talk about the oxidation states, the d block elements, they show a wide range of oxidation states, basically depending upon their electronic configuration. Whereas in case of f block, most stable oxidation state will be +3, and then others can have, other oxidation states can also be available, but the most stable one is +3. Then in d block, you can say that almost all the elements, they are about, they are stable. But in case of f block, if you check the f block, you will find mostly radioactive elements present in f block. Then in d block, this can either be transition elements or non-transition elements. Then in f block, there are two series. Okay, one is lanthanoids and the other one is actinoids. There are two series in f block. Now in d block, they have partially or completely filled outermost d orbitals. Now over here in f block, unified by having one or more of their electrons, outermost electrons, in the f orbital. Okay, so this is not a very important point, you can say. So till here you can note down, till this point. Okay, so note down all these d block and f block comparison. So with this we come to the end of this video, and I hope you found this video really helpful for your revision. From the revision point of view, I had made this video covering almost all the important topics briefly. So if you want more of such videos, then please let me know in the comment section below. And then if you like this video, please press the like button and don't forget to subscribe my channel also. So thank you for watching this video and meet you in my next video.